Hi students, this is Satish Kumar. Today we are going to see the different types of charge distribution. In the last lecture, in these types of charge distribution, already we have completed the point charge distribution as well as line charge distribution. The point charge distribution, we have even seen the electric field intensity expression as E equal to Q by 4 pi epsilon R square AR vector. And for the line charge distribution, we have defined a very important parameter called line charge density. We have defined it for both uniform and non-uniform charge distribution. And we have even defined the expression for the electric field intensity, which is a line integral of rho L dl by 4 pi epsilon R square AR vector. This is the expression for the electric field intensity due to line charge distribution. We will extend, this is actually for a finite line charge distribution, and by taking the limits from minus infinite to infinite, we can extend it for infinite line charge distribution. Now, we are going to see the surface charge distribution and volume charge distribution. First, we'll start with the surface charge distribution, which is the third type of charge distribution. Surface charge distribution. In this surface charge distribution, let us take a surface which need not to be a square kind of shape. It can be of any shape. On this surface, which is actually a metallic sheet, we have to assume it as a metallic sheet. And on this, you distribute positive charge. And similarly, you take another surface of circular shape. Okay, and distribute negative charge on it. Negative charge on it. And let us assume that the total charge on this surface is plus Q. And the surface area of this is, let's say, S. Similarly, here as the charge is negative, so we can say the total charge on this is minus Q, and the area again is denoted by S. We may know the expression area of the surface, but we will first write it just with the representation S. Now, there is a very important parameter which is related to this surface charge distribution, which we call it as surface charge density. Let us try to define first what is surface charge density. Before that, let us try to define first what is surface charge distribution. The charge which is distributed on any sheet or any surface, we call it as surface charge distribution. That is the definition of surface charge distribution. Now we will try to define the definition of surface charge density. Surface charge density. Again, there will be two cases here. The charge, if you look at in both the surfaces, is it uniform or non-uniform? Initially, after distribution, the charge may look like uniformly, because in every area, the charge may be equally distributed, every 1 meter square area, we can say. But because of the repulsion between these positive charges or negative charges, the charges which are distributed on that particular 1 meter square of area may be different. So because there will be always two cases we will get. First one is uniform charge distribution, which is generally not possible but we have to discuss. So first we'll try to see uniform charge distribution. Uniform charge distribution. For the uniform charge distribution, we will define this rho s as, which is the surface charge density, as it is the total charge on this is plus q and total surface area here is s. So it is always the ratio of total charge on the surface, total charge on the surface to the total surface area, total surface area. Now let us try to denote this. What is the total charge? Let's say plus q by the total surface area is s. So we can even call that rho s is also a positive charge density. The unit of charge is coulomb and the area is always meter square. So the unit of surface charge density is coulomb per meter square. But this is for the case of uniform charge distribution, uniform charge distribution. So if you want the total charge which is present on that particular surface will always be calculated by using the product of surface charge density into the total surface area. You will get them in coulombs. And let us take how this is possible. Suppose you take some surface and distribute charge on it. Distribute charge on it. So because you are seeing for the uniform charge distribution, assume the charge is uniform in the entire surface. Now what you do is divide this surface into equal parts. If you observe, this is 5 rows and 4 columns, so there will be 20 squares we got, and this total area is, let's say, 20 meters square. That means every square you will be getting exactly 1 meter square. 1 meter square, and this is also 1 meter square. Each and every square area is 1 meter square. Then the surface charge density is, let's say, 5 nano coulomb per meter square. This indicates, as it is a number, this indicates on 1 meter square area there is a charge of 5 nanocoulombs. That means in this every 1 meter square area the charge which is distributed is 5 nanocoulombs. Then how much is the total charge which is present on it? That is q is equal to rho s into s. There rho s is 5 nanocoulomb per meter square into that total area is 20 meters square. So here meter square gets cancels, 100 nanocoulombs. This is the charge which is present. So this is a very simple question that we can get it. But as I said, most of the cases, we will get non-uniform charge distribution. Non-uniform charge distribution. For this non-uniform charge distribution, how do we define this charge density, rho s? It is always equal to the ratio of differential charge, ratio of differential charge to the differential surface. Differential charge to the differential surface. This we can write it as differential charge is denoted by dq and differential surface is with ds. Again the unit will be same, coulomb per meter square. So from this, what we get is dq will always be equal to rho s ds, as it is the differential surface. So if you want the total charge, you should always prefer taking a surface integration. So this is a dq. So taking surface integration on both sides, what you will be getting is surface integral of rho s ds. And this surface integral of dq will be simply q, which is equal to surface integral. Either you write a single integration and suffix s, or else you can take the surface integral always means it's a double integration. It's a double integration. You can write like this, rho s ds. When you take double integration, there is no need to place s at this. So this is what is the expression for the charge when non-uniform distribution is given, charge distribution is given, like rho s is equal to something like some x into y nano coulomb per meter square, or something like in terms of cylindrical coordinate system, which may be in terms of rho phi z, that is rho z nano coulomb per meter square, something like this. The questions, and here rho and z limits will be given to you so that you can able to get the total charge. Okay, so we'll try to see problems on this. Now the next part will be, what is the electric field intensity due to surface charge distribution? What is the electric field intensity due to surface charge distribution? We'll try to again take the same surface. On this, you distribute the charges. The charges here may not be uniform, they are random, because we'll be finding out the expression for the non-uniform surface charge distribution. The total charge on this is, let's say, plus q, and its surface area is s. And you have a very strong electrostatic field around this. You have a very strong electrostatic field here. Suppose you want to find out the electric field intensity, okay? But you cannot directly get the electric field intensity with this entire sheet of charge. So what we have to do is, we know only one expression before that, that is E due to point charge. And that E due to point charge is E equal to Q by 4 pi epsilon R square AR vector. That means this is a point charge where you have to get the same kind of point charge in this surface. As this surface is a very big surface and the total charge on this is plus q, we need to get a very small charge. How do we get a very small charge? By taking a small differential surface. This we call it as a small differential surface, and this is a vector quantity because this particular surface direction is normal to it, and that we call it as ds. So because of this differential surface, the charge on this is, let's say, plus dq or simply dq. So this dq is a point charge. The dq, we should consider it as a point charge, which is actually a very small charge. That small charge is also called point charge. So dq is a point charge, and due to that point charge, because we have already an expression for E due to point charge, we will have to find out the electric field intensity due to that point charge. Let us try to draw a line which is joining them. So this distance, let us call it as r, or small r or capital R. Just for convenience, I'll be taking it as capital R. I'll tell you, because while seeing the derivation of E due to infinite sheet of charge, you may get confused with the small r and capital R. That's the reason I'm taking it as capital R. And the unit vector in this is AR. Okay, so this is how we have to find out. But due to this entire sheet of charge, we will get the total electric field intensity, which is E vector. But due to this small differential charge, we don't get the total. What we get is only differential electric field intensity. Now we will try to write the expression for dE, which is equal to, here the point charge is Q, but here the point charge is dQ. So we'll try to write dQ by 4 pi epsilon. Here I'm taking capital R square and AR vector. But you want the total electric field intensity, so you will have to extend this differential surface in all the 4 directions because you know the dimensions, and that will be done by using surface integration, which is a double integration. If you take surface integration on both sides, you will be getting surface integral of, what is this dq will be? Dq, we have already got an expression which is rho s ds. We'll be substituting that. So dq will be equal to rho s ds by 4 pi epsilon r square ar vector volt per meter. So therefore, we will get the total electric field intensity equal to surface integral of rho s ds by 4 pi epsilon r square ar vector volt per meter. This is your expression for finding out E due to sheet of charge. Okay, so we'll be doing the volume charge distribution, okay, in the next class. So if you like my videos, please subscribe to my channel. You are going to get the entire electromagnetic field, which includes the transmission lines and waveguides. And also I'll be solving the problems in gate level as well as in engineering level. Thank you very much.